thank you, Professor Yu, for the introduction. Yeah, thank organizers give me this opportunity to speak here. Yeah, right. So my talk will be the continuation of Professor Dai's talk. Yeah, we'll continue to talk about positive mass theorem and also positive scatter geometric with isolated conic singularities. Right. This is all enough now of my talk. We'll still very briefly review the classical positive mass theorem, and then we'll look at our main result again, and finally look at the proofs of our results. So Professor Dai has given some general picture for what we did and the motivations, and also indicated the main ideas. So I will try to fill in some details for these things. Okay. So let's still start with the asymptotic flat manifold. Okay, that's a complete smooth manifold, and it has a compact set, and the complement of this compact set consists of finite many ends, and each end is diffeomorphic to Rn minus a ball. And so on each end, we have a global correlated system. And on each end, the remaining metric G is asymptotic to the Euclidean metric. That is Euclidean metric plus perturbation term H. And the asymptotic order, the key order for H, we require that to be greater than half of -2. And
William, what's your summer plan?
Sorry.
Whoops.
Oh, okay. Can you talk to me?
William, what's your summer plan?
Oh,
sure. Okay. Yeah. So we also assume the scatter curvature to be L1 integrable. Okay. And under these assumptions, we know the so-called ideal mass is a invariant of metric G.
I think okay, sorry, my microphone is off. That's the reason. Okay.
Okay. Yeah. Right. All these things Professor Dai has explained not, so let's just look at the definition, and now look at two simple examples. Of course, the simplest example should be the Euclidean space. It has one end, and clearly its mass is 0. Okay, and then a trivial example is Euclidean Schwarzschild manifolds. So now the manifold is Rn minus origin, and the metric is given by this conformal deformation of a Euclidean metric, the conformal factor. So here R is the Euclidean distance from a point to the origin, and we can see when R goes to infinity, this is a conformal factor tends to 1. So and Euclidean infinity we have a asymptotic flat end, and for R going to 0, the conformal factor blows up, right? So this conformal factor is relevant to blows up the origin to an asymptotically flat end. So for this manifold, we have two asymptotically flat end, and it's a scatter flat, and for the ideal mass for both ends 2 times m, and for m if m is negative, then we get a so-called negative mass Schwarzschild metric. That was example discussed by Professor Dai. Right. Okay, so this He is very important example. Okay, and now the classic Porte-Masse theorem says for asymptotically flat Riemann manifold, if scalar curvature is non-negative, then ideal mass is non-negative, and rigidity says mass equal to zero. Manifold has to be uh, asymmetric to the Euclidean space, right? And here are some remarks for the proofs, but yeah, since I think Professor Dai has explained this actually some in details, so let's just go with this. Right. And so now we move on to the singular manifold we work on. Right, so it's a manifold with oscillated conic singularities. Okay, so this kind of singularity is modeled on this so-called model cone. For that, we have let's say we have a smooth closed manifold N, and we have remaining smooth remaining metric on that GM. The model cone is just a product manifold, and we give a warp product remaining metric on that. So warping function is R. R is a correlate on this interval. And when you see a remaining manifold with oscillated conic singularity, we mean it's a singular manifold, and its singular set consists of finite many points, and near each singular point, the remaining metric G is asymptotic to the model cone metric. That is the sum of multiple metric with some perturbation term H, and we have some decay control for the for this perturbation term H, and now we see asymptotically flat manifold with oscillated conic singularity means this manifold can be separated into two parts. One part M0 is a compact manifold with oscillated conic singularity, and M infinity, and the rest of that consists of finite many AFNs. Right? So basically, it looks like this. If we have this just one singularity, but we can have multiple. We have multiple conic singularities. So this cross section, and we can say if this kind of conic singularity in general is not only metric singularity, but also topological manifold singularity if the cross section is not diffeomorphic to sphere. Right. Now, even this diffeomorphic to sphere metric Gn may not be rounded standard round sphere metric. That's just a conic, just a metric singularity. Okay. So, and more generally, we also looked at the Hall singularities modeled on this kind of model Hall. Right, so warp the product metric, also product manifold into with a cross section N, and when b equal to 1, this recovers model cone, and so lective mass Schwarzschild metric can be viewed as a asymptotic flat manifold with a Hall singularity. So now here b is 2/3. So, okay, so this example discussed by Professor Dai. Okay, so now our first result is the Porte-Masse theorem is oscillated conic singularities. Right, that says, yeah, in for the AF manifold with find many oscillated conic singularities, Porte-Masse theorem still holds, and we also got rigidity. Right? So And for the whole singularity, right, with some B is strictly greater than 1, and the Yamabe invariant of the cross section is strictly greater than 0, then we can get to the positivity of the mass if assume the scalar curvature is non-negative. And in dimension 3, Miao's mass capacity equality so implies positive mass theorem for B strictly greater than 3 over 2 in the whole singularity case. So this this result should be the sharp result for the in dimension 3, because we know three-dimensional negative mass structured metric has a whole singularity with B equal to 3 or 2. And I think in general dimension we should be able to get similar sharp result. Yeah. Okay, so then our next result is about the non-existence of a positive scalar curvature metric with conic singularity. So first recall the classic abstraction of positive scalar curvature matrix for the complete smooth metric. So the first is a resolution of Geroch conjecture that says there's no complete positive scalar curvature metric on torus, proved by Hirsch-Miao for dimension, I think, 7, the grammar of Lawson for arbitrary dimensions with a Dirac operator method. And actually, grammar of Lawson proved modes for the collected sum of torus and compact spin manifold. And this torus can be replaced by the error inarguable manifold. It's a very important concept introduced by grammar of Lawson. And in recent years, there are some extensions for grammar of Lawson's work. So, first is one is by Xianzhe Wang and Professor Witten. They extend spin manifold M to be non-compact. And another is by Chodosh-Li. Yeah, it's for arbitrary M, but dimension is okay. I think as Gromov remarked, this should be less than equal to 8, right? And also in dimension 3, it's proved by Nasod and Yao. All right. So now, based on these extensions of Gromov-Lawson result in the non-compact case, yeah, then we can get some non-existence result for positive scalar curvature metric with conic similarities. So now let's see we have a compact smooth manifold M, and we have some dimension that's equal to 7, or it's a spin of arbitrary dimension. Right. So then collect sum M with collect sum of M with torus does not admit positive scalar curvature metric with oscillating conic singularities. And we also have rigidity result. It says such a conically singular metric with a non-negative scalar curvature must be flat, and so it's smooth. So, and here we can now in the theorem as stated here, we assume M is a compact smooth manifold, but more generally we can have topological conic singularity. Right? For example, the M manifold M could be a manifold with boundary, right? And we could collect the sum of that with torus, and then we can, for example, to pinch the boundary to a point at the tip of the cone, actually, right? So get the conic singularities, and so then right. So our result shows So this kind of conically singular metric with positive scalar curvature cannot exist. Yeah. So in even dimensions, the other Chow extended Gromov-Lawson's work to the isolated conic singularity case, proved the non-existence of a positive scalar curvature metric on area in algebra closed manifold with the isolated conic singularity. And more recently, Shi and Tam proved the similar result on the torus. So non-existence of positive scalar curvature metric on torus with isolated conic singularity. Their cross section is a scaled round sphere. All right, so these are our main results. Okay, so now let's move on to proofs. Since in our proof, we'll need to use a positive mass theorem for EF manifold with boundary, or positive mass theorem for with arbitrary end, asymptotic flat manifold with arbitrary end. So let's recall some this result first. So now let's say we have a asymptotically flat manifold with boundary sigma, and scalar curvature is not negative. So now use H to denote the mean curvature of the boundary with respect to the normal vector pointing to asymptotic flat end. Okay. And so now the Gibbons-Hawkins Horowitz-Perry extended Witten's argument on the assumption that H, the mean curvature, is non-positive. In this case, we got a positive mass theorem.
One question. Can I ask one question? So is the boundary assumed to be compact, or can it be non-compact? The boundary.
Oh, you mean here? I think it's compact.
Okay.
Yeah, I'm not 100% sure, but yeah, it's compact. Yeah, it should be compact. Okay, and so yeah, so then later, Hertz generalized this result to allow the mean curvature to be positive, but satisfy some upper bound condition in terms of Yamabe invariant. This is why sigma g is the Yamabe invariant of the boundary sigma. Yeah. So in three dimensions, it's just bounded by this term involves area of the boundary. And so from this, actually, yeah, it's not. Yeah, we can get the positive mass theorem for the R for the whole singularity for b greater than equals 3 b greater than 1. Yeah, it's just calculate the mean curvature of the boundary. Yeah, look at the power of the R. Okay, and then okay, and so now the more recently, Hirsch and Miao also proved the positive mass theorem is boundary. Yeah, so right, so so their mean curvature can also be positive, but still satisfy some upper bound condition. So their upper bound in terms of the derivative of harmonical function. So, and in particular, their result also implies the positive mass theorem for non-positive mean curvature. So basically, we can say if the main curvature of the boundary not too large, then positive mass theorem still holds. Okay. So this is a positive mass theorem for the asymptotically flat manifolds with boundary. Okay, and another thing we can use is a positive mass theorem for asymptotically flat manifolds with arbitrary end. So for this, basically is so asymptotically we have asymptotically flat end and also some other ends, right here. Yeah, maybe some other ends, and the ADM mass is on the asymptotically flat ends. So yeah, so by the this is proved by the sort angle yaw, and also Zhu they use different method. The sort angle yaw use the mu bubble method. Yeah, so here's still for is between 3 and 7, and Zhu used the low-cap compactification, and also the Chodosh-Li's resolution of generalized Geroch conjunction. So the result I just mentioned. So that's for the non-existence of positive scale curvature metric. So okay, so this is the main idea for our proof. Actually, Professor Dai has just talked about this. So let's briefly recall that. So basically now we have asymptotic flat manifolds with conic singularity. So now main thing is to blow up this conic singularity to the to an asymptotically conical end. So and basically it keeps this asymptotically flat end, and we just by doing some this is for this we're doing a conformal change of the metric G. It's the use this conform change, right? And this conform change is like flip the cone, change the cone tip to the cone end, and so the main thing is we need to solve this kind of harmonic function on asymptotic flat manifolds with conic singularity, right? And after we do this, we actually we can directly get the bottom theorem from the sort angle Yaw's result, or Hirsch-Miao's positive mass theorem with boundary. Okay. Yeah. So and for the rigidity, yeah, we first get this ridge flat. This is similar as the classical case, and then we construct a asymptotically Euclidean harmonic correlate. So basically, we still need to solve some harmonic function, right, with some prescribed asymptotic and asymptotic end, on the asymptotic end, flat end, and then we'll get the rigidity for the cross section, right? So that cross section has to be standard sphere. Then we'll get the metric G, our conically singular metric G will be in W12. Have W12 regularity, so that we can apply the junction result, or Lee and Lovelock's result, right, for the positive mass theorem with low regularity. Okay, so yeah, so that main thing is solving some harmonic functions, right, on the asymptotic flat manifold. But let's look at some analysis on this kind of single manifold. So now we know the Sobolev spaces are very important tools for solving the elliptic equations on the compact manifold. So now we just use some weighted Sobolev spaces for this kind of singular and non-compact manifold. Right? So now we need to add some weight, and both near both conic singularity and also asymptotically flat n. So one is one you have two index delta and beta. The delta is for the conic singularity and the beta is for asymptotic flat n. So so R is a radial vector. So the radial correlate on the conical singularity, and the rho is Euclidean distance on the asymptotically flat end. So we give this kind of weight for the Sobolev law, and so this kind of weighted Sobolev law has very nice homogeneity property when we do the scaling for the function along the radial direction of the cone or the asymptotic flat end. Right? So by this, one can actually easily obtain this kind of weighted elliptic estimate. Right? So this is not it's very standard, but this kind of weighted elliptic estimate is not not very useful in solving the equation, right? Because from this we cannot get a Fredholm property or it's kind of nice property for the operator, because this space is not compactly embedded into the LP delta beta. Right? In order to get compact embedded, we need this delta and this beta should be different from this the delta beta index in W2P space. So for that, we need to get some refined weighted elliptic estimate. But then we need to rule out some index, right? The so-called critical index. This critical index depends on the eigenvalues of the Laplace operator on the cross section, right? So if lambda g eigenvalues of Laplace operator on cross section, then it defines mu g plus or minus like this. Right? So this basically can be solved by looking at this thing. So it's mu g plus or minus times phi g. So phi g are eigenfunctions on the cross section. Right? And if we look at this thing, solve this equation, we'll get mu g. Looks like this. Right? And for the if the cross section is a standard sphere, so eigenvalues are clear, so we can get mu g plus or minus will be g or 2 minus or minus g. So then we say index is delta beta is a critical. If that's a critical and the conic singularity, or it's critical and asymptotic flat n. So so if we have a pair of indices delta beta is not critical, right? Then we can get this kind of refined elliptic estimate. Right? So weighted elliptic estimate. So now B is a compact set, right? So in other words, here we can put this index delta prime and beta prime, as delta prime and beta prime could be any number as we want. So then actually this space is not this space is compactly embedded into L2B, right? So from this we can get the Friedholm property for the Laplace operator, right? And right, this refined weighted elliptic estimate, so on the asymptotic flat end was derived by some very nice and elementary calculations by MATLAB. And from this calculation, we can see why we need to rule out this critical indices. And of course, this kind of thing can have some other explanations by using big calculus of Marius and Mazel, and some other people. Okay. So, right. So now we want to solve harmonic equation, so we can we consider this unbounded operator. And so now from the refined weighted elliptic estimate just mentioned, then if it's index delta and beta not critical, then we get this operator Friedholm. So then we ought to show it's subjective, just need to show it's drawing is injective, right? This can be done if you assume delta is less than half of 2 minus n of and the beta is greater than half of 2 minus n, right? These are okay, but this region is not so for so this region of delta and beta actually not good enough for us to solve the equation as we need. So we need to extend the region for delta and beta so that we can get the subjectivity of this kind of operator. Right? For that, let's look at the so-called decay jump property. It's called by Minab. He got this kind of property on the asymptotic flat end. All right. So that says if we have this equation, it's Laplace for u equal to f, and assume f is in L2 delta prime minus 2. Right. So then we should expect to get u in L2 delta prime, right? But clearly this solution of this kind of equation is not unique, and the difference between the two solutions should be a harmonic function, right? And we know this thing, all right? So if we use a spectrum decomposition on the cross section, then we can see the kernel of this harmonic functions, right, on the cone can be written as this, right, on the sum of these kind of functions, right? So then we can see if the solution of u will be some function. So we in L2 delta prime, that is what we expected, what we want, and also plus some functions like this, right? But this so exponent between delta and delta prime, right? And then very nice effect is that we don't have a critical index between 2 minus n and 0, right? 2 minus n and 0, and we already show that for I think that's less than this, right? So it's near the cone, and for the index and the conic singularity, the delta, if delta is less than this number, we know it's and the non-critical, we get subjectivity of the Laplace operator. And so now by using the decay jump property, we can extend this to this region, right? So less than equal to zero, less than zero, strictly less than zero. And for the for the index and for the index and asymptotically flat infinity, we get we can extend that to be 2 minus. So now we get subjectivity for the Laplace operator for non-critical index delta beta. So at delta is less than zero, and beta is greater than, strictly greater than 2 minus n. Then this region will be good enough for us to solve the harmonic equations, so harmonic functions that we need. Okay. So right. So basically, for the non-negative of the mass, we need to solve the equation, solve harmonic function so that U looks like 1 over R minus 2. This is basically like the Green's function centered on the conic singularity, right? So we start with this function. Basically, that means we prescribe the asymptotic behavior near the conic singularity and solve this solve the harmonic function, and then we can use some weighted elliptic estimate and weighted sublapping band of these techniques to get the asymptotic control near the infinity. It's 1 plus something. So 0 minus 2a. And when we prove the rigidity, we need to solve the harmonic function. We need to solve the harmonic function that is asymptotic to the Euclidean coordinate, right? And infinity. And so for this, so in this case, we prescribe the asymptotic behavior and asymptotically flat end, and then we solve the harmonic function. And then we need to have some process asymptotically expansion for this harmonic function near the conic singularity. So this is some power times like this, and this so this thing will collect the asymptotic behavior of the kind of harmonic function with the geometry of the cross section, so that we can get to the rigidity of the cross section and finally get the rigidity of the rigidity result for us. Okay, and okay, so this is basically this is proof for the main ingredient we need in the proof of four-point mass theorem, and it's non-spin case. And for spin case, we extended the Witten's argument, right? So for that, we need to solve the Dirac equation, so we can do something similar actually as this Laplace operator. Right? So now, let me say some words about proof of non-existence of positive scatter curvature metric with oscillating conic singularity. So, right. So now so the case is still to blow up the conic singularity to get some complete metric. So, but now our manifold is compact, right? It's compact, so it's sort of different, right? So let's say we have a conic singularity here, and right. So now we can not expect to have harmonic function on this compact manifold with conic singularity, so that the asymptotic behavior near the conic singularity to be this, right? Since we can get a contradiction from the maximum principle easily, right? So before we do blow up, we need to use a Gromov-Lawson's surgery to get non-compact manifold with conic singularity. So in particular, asymptotic flat manifold, we can get an asymptotic flat manifold with conic singularity. So now, depending on the position while we do the surgery, we need to do that. We need to deal with two different cases. If the scalar curvature is a strictly positive near the conic singularity, okay, then we can just do the surgery, for example, here, and get asymptotic flat manifold with conic singularity. And then we on this kind of manifold, we have solved harmonic functions as we want to blow up the conic singularity to a conically asymptotically conic end. Then we can apply the Chodosh-Li and Wang-Zhang's result to get non-existence result, get contradiction. Okay, and so another case is another case is if the scalar curvature near the conic singularity is identically zero. So in this case, we cannot do surgery here near the conic singularity, right? So if we do surgery and, for example, this kind of point, then right, we will then after we blow up, we basically we will change the collect sum, right? So probably we will get collect sum of like this, right? Then yeah, maybe we cannot apply the result of Chodosh and Li. So so in this case, but good thing that now we can solve the conformal Laplace equation, right, to get a function, so that we can conformally blow up the conic singularity of that function. And in this case, we solve this conformal Laplace equation. The assumption that the scalar curvature is identically zero near the conic singularity is actually very important for us. Right? Okay, so and for the rigidity, so basically we still I think the basic idea is the same as a classic case. We first get from the we assume that the scalar curvature is zero. So first we will get the Ridge curvature will be zero. Yeah. So basically, if the Ridge curvature is not identical to zero, then we can deform the metric to get a positive scalar curvature metric with conic singularity. And after we get this, then we can use some rigidity result in RCD space to get the to get our rigidity result. I think that's all I want to say. All right. Thank you very much for your attention.